So at the end of the last lecture segment, I suggested you try quiz 4.6, and now we'll solve it here in case you had any problems with it. So the first thing we're asked to do is sketch the PDFs of x, the Gaussian 0, 1 random variable, and y, which is Gaussian 0, 2, and we're supposed to do this on the same axis. So we start by trying to draw a nice straight axis, and then we draw a bell-shaped curve, and then we know that random variable x has expected value 0, so the center of the bell-shaped curve should be at x equals 0. So we'll mark the center and label it 0, axis x, draw y-axis, and label this fx of x the PDF of x. We know that fx of x is equal to 1 over root 2 pi times sigma squared, but sigma squared is 1, e to the minus x squared over 2. And thus we know that the PDF of x at x equals 0 is 1 over root 2 pi, which is approximately 0.4. So maybe we'll label this 1 over root 2 pi. And now we'll choose a different color ink and try to draw the CDF of y. So y is also Gaussian. The mean is 0, but its standard deviation is 2. So we can write down the PDF of y. Fy of y is 1 over square root of 2 pi. And now we have sigma squared, but sigma equals 2. So it's 2 pi times 4, e to the minus y squared over 2 times 4. Put it another way, it's 1 over square root 8 pi e to the minus y squared over 8. And what we know from that is that fy of 0 is equal to 1 over 8 pi, which equals 1 over 2 times square root 2 pi. So it's exactly 1/2 of the PDF of x at 0. So now we're ready to sketch the PDF of y. We know that the peak value is half of the PDF of the peak value of the PDF of x. So we make a little dot. And then we draw a wider, lower Gaussian random variable, Gaussian PDF. My sketch isn't very good, but the thing that's supposed to be true is that both the black curve and the blue curve both have area under the curve of 1. But y, which has bigger variance and twice the standard deviation, is much lower and broader. In short, the spread of the PDF of y is twice the spread of the PDF of x, because it has twice the standard deviation. Now we're ready to use theorem 4.14 to solve for the rest of the parts of the quiz. Remember, theorem 4.14 says that the CDF of x, when x is Gaussian with parameters mu and sigma, is equal to the phi function of x minus mu over sigma. Right? In our example, x is Gaussian, mu is equal to 0, sigma is equal to 1. So the CDF of x is just equal to phi of x minus 0 over 1, which is just phi of x. In the same way, we know that since y is Gaussian, the CDF of y is equal to phi of y minus mu over sigma. But in the case of y, mu is equal to 0, but sigma is equal to 2. And this equals phi of y over 2. We can now use these facts to solve for parts A, B, C, and D. Specifically, for part A, we write that the probability x is in the interval from -1 to 1 is the CDF of x at 1 minus the CDF of x at -1. This is phi of 1 minus phi of -1. And then you may remember an identity that phi of -1 is equal to 1 minus phi of 1 that we showed earlier. And so we get 2 phi of 1 minus 1. If you go check the table, you'll see that phi of 1 is equal to 0.8413. And so our result is 2 times 0.8413 minus 1, which is approximately 0.68. Since x has standard deviation 1, this 0.68 is special. It's equal to the probability that x is within 1 standard deviation of its expected value. Now we take the same steps in part B for y. So the probability that y is between -1 and 1 is the CDF of y at 1 minus the CDF of y at -1. And this is phi of 1 over 2 because the CDF of y is equal to phi of y over 2 minus phi of -1 over 2. And using the same identity for negative values, this is 2 phi of 1/2 minus 1. If you check the table, phi of 1/2 is equal to 0.6913. And so this is equal to 2 times 0.6913 minus 1, which is approximately 0.38. For part C, we observe that the probability x is greater than 3.5 is equal to 1 minus the probability x is less than or equal to 3.5. It equals 1 minus phi of 3.5. The problem is that phi of 3.5 isn't in our table. And so in fact, it's actually better to have skipped these steps and instead just observe that because x is Gaussian with mean 0 and variance 1, the probability x is greater than 3.5 is in fact equal to q of 3.5. Consulting with the q table, we find that q of 3.5 is equal to 2.33 times 10 to the minus 5. Finally, we observe that the probability that y is greater than 3.5 is equal to 1 minus the CDF of y. 3.5 is 1 minus phi of 3.5 over 2. It's 1 minus phi of 3.5, 1.75. Consulting with the table, this is 1 minus 0.9599, which is equal to 0.401. We solved the quiz using theorem 4.14. And at this point, it's instructive to go back and kind of understand what its power is. In fact, theorem 4.14 does more than just allow you to solve for probabilities about Gaussian random variables. We derive theorem 4.14 using calculus and a little bit of algebra, but in fact, it says something kind of significant. If we write it backwards, we have that phi of x minus mu over sigma is equal to the CDF of x, and that's equal to the probability that x is less than or equal to x. Now we'll do some algebra to express this a different way. Our first step is to say that the probability x is less than or equal to x is the probability x minus mu is less than or equal to little x minus mu. And then because the standard deviation is non-negative, we can say that this is the probability x minus mu divided by sigma is less than or equal to x minus mu over sigma. Now, x minus mu over sigma is just a random variable since x is a random variable, and we could give it a new name, y. So let's let y equal random variable x minus mu over sigma. And so we have this is equal to the probability y is less than or equal to little x minus mu over sigma. And this is just the CDF of y at x minus mu over sigma. So what we obtain is that the CDF of y at x minus mu over sigma is equal to phi at x minus mu over sigma. But this x is a dummy variable, and x minus mu over sigma can be any quantity. So in fact, what we've shown is that the CDF of y for any value of y is equal to phi of y. But what that implies is that y is a standard normal random variable. That is that y is Gaussian with mean 0 and variance 1. In terms of x, we have that if x is Gaussian with parameters mu and sigma, then x minus mu over sigma is Gaussian with parameters mu equal to 0 and standard deviation sigma equal to 1. In the derivation of this result, we use the letter y to denote x minus mu over sigma. But in fact, it's more common for us to write x minus mu over sigma and call it z, because z is what we use for the standard normal Gaussian. It's also worth noting that for any random variable x, x minus mu over sigma has expected value 0 and variance 1. To see this, let's write E of z is equal to E of x minus mu over sigma. And that's equal to 1 over sigma times E of x minus mu. But E of x minus mu is equal to 0. And for the variance of z, we have it's equal to the variance of x minus mu over sigma, which is equal to 1 over sigma squared times the variance of x minus mu, which is equal to 1 over sigma squared times the variance of x, but the variance of x is sigma squared, so this equals 1. So in general, if we take a random variable x and subtract the mean mu and divide by the standard deviation sigma, we get a random variable which has zero mean and unit variance. And if x happens to be Gaussian, then x minus mu over sigma is also Gaussian. So now let's revisit quiz 4.6. So now let's revisit quiz 4.6 and remember that y is Gaussian and mu y is 0 and sigma y equals 2. In this case, the probability that y is between -1 and 1 is equal to the probability that -1 minus mu y is less than to y minus mu y is less than or equal to 1 minus mu y. And this is equal to the probability -1 minus mu y over sigma y is less than y minus mu y over sigma y. It's less than or equal to 1 minus mu y over sigma y. And now what we see is that this quantity in the middle here, this is a standard normal random variable z because we subtracted away the mean and divided by the standard deviation. And so now plugging in mu y and sigma y, we get the probability that this is -1 minus 0 over 2 is less than z is less than or equal to 1 minus 0 over 2. So we have the probability that the standard normal Gaussian is between 1/2 and -1/2. And of course, this equals phi 1/2 minus phi minus 1/2. And this is equal to phi of 1/2 minus 1 minus phi of 1/2 to phi of 1/2 minus 1. So we could look up phi of 1/2, or we could remember it from earlier in this video. But in fact, if you're taking an exam, a perfectly fine answer is just to write 2 phi of 1/2 minus 1. We won't ask you to remember any values from the phi table.